Alright, so we are still in section 7.5 and we're still talking about operations of radicals. This second video is going to look at some more of the complicated radical operations, basically the ones that involve binomial radical expressions. So we're going to call this video binomial radical operations. Okay, there's only a few that I need to talk about with you. They're kind of offshoots of what the first video talked about. So the first one I'm going to talk about is foiling with radicals. Okay, so if you see an example like this, we've got 6 times the square root of 3 minus 5 times 2 root 5 plus 4 root 2. So you've got two binomials here. Each one of them is its own number, but it sort of looks like a FOIL problem, right? So we're going to do this the same way we have done FOIL before. We'll do the first two terms, we'll multiply them together. So 6 root 3 times 2 root 5 is 12 root 15, because we do outside and inside numbers separately. Then we'll do the outer pair, and that's going to get me plus 24 root 6. Then we'll do our inner pair. That's going to get me negative 10 root 5. And then we'll do our last two terms, and that'll get us negative 20 root 2. Okay? So our next step would be to see, can I combine anything? Are there any like radicals? Is there anything that I can simplify? For this problem, it turns out there isn't. And a lot of times that's going to happen with FOIL. This whole monstrosity ends up being the final answer. And it's just because we can't really add radicals unless the radicands are the same. Okay? Let's try another one. Let's do one that's a little bit more special. Let's do 3 plus root 2 times 3 minus root 2. Okay? Again, we'll FOIL. So we'll do the first two terms together. 3 times 3 gets us 9. Our outer product is negative 3 root 2. One's on the outside, one's on the inside. So they really don't multiply. They just kind of get stuck together. Our inner, same thing. We get a positive 3 root 2 this time. And then our last is root 2 times negative root 2, which is negative root 4. Okay, there is some stuff that can simplify here, so let's clean it up. My middle two terms, my negative 3 root 2 and my positive 3 root 2, they actually combine and they cancel because negative 3 and positive 3 gets me 0. Okay? The square root of 4 is 2, so this becomes 9 minus 2, and what do you know? My final answer is a whole number, it's 7. That will sometimes happen, especially because these two terms that I multiplied each other by are special terms with each other. They're called conjugates. Okay, we've seen that word before when we talked about complex numbers and conjugates. Remember a plus bi and a minus bi? This is sort of the same idea, except instead of an I, we have a radical. So if you think about it, 3 plus root 2, 3 minus root 2, the individual terms in the binomial are the same. However, the only difference is the middle sign. Let's do another example. Let's do another type of problem. Let's talk about rationalizing the denominator again, but let's go back to something that's a little bit more complicated. Let's do something where the denominator is a binomial. So I've got 2 over root 5 minus 1. Now, if I tried to multiply the top and bottom by root 5, I would not get rid of it. The reason is I'd have to multiply root 5 by both terms in the denominator. And while the root 5s would cancel out in the first part of the binomial, I'd also have to do negative 1 times root 5, and that will still be a radical. So instead, what I'm going to do is I'm going to multiply by the conjugate of my denominator. So the conjugate in this case is going to be root 5 plus 1. So that's what I'm going to multiply here, top and bottom of my fraction. Okay? So when we do our numerator, we distribute the 2 into both terms. We get 2 root 5 plus 2. When we do our denominator, we FOIL. So first is root 25. Outer is positive root 5. Inner is negative root 5. And last is negative 1. Okay, the top I can't do much with, so I'll just carry it through. The bottom I can. So the root 25 becomes a 5. The positive root 5 and the negative root 5 in the middle cancel, and minus 1's already a number, so 5 minus 1 gets me 4. And then look, I actually do just a little bit more to this problem. I can take these 2's and that 4 and divide it all out by 2, and now I get the square root of 5 plus 1 over 2. And that's my final answer for that one. Okay? Let me do one more like this. So let's try something a little bit more complicated looking. So we've got 2 root 2 plus 2 root 5 over root 5 plus root 2. So I've got a binomial with 2 radicals. All right, we'll do the same thing we did before. We will multiply top and bottom by our conjugate. So in this case, that's going to be root 5 minus root 2. We keep the roots the same. All we change is that middle sign. And now we can do some foiling. So we'll FOIL the top. It's going to be 2 root 10 minus 2 root 4 plus 2 root 25 minus 2 root 10. In the bottom, we get root 25 minus root 10 plus root 10 minus root 4. Now there's a lot that's going to clean up here. So I've got a 2 root 10 and a negative 2 root 10 up top. I'll cancel those out. I've got a 2 root 4 in this second term, but root 4 is just 2, so it's negative 2 that's already here times another 2, which gets me negative 4. I've got 2 root 25, which is really just 2 times 5, so that becomes plus 10. So my top turns into a nice integer. My bottom will as well, because the negative 10 and the positive 10 cancel. Root 25 is 5, root 4 is 2, 5 minus 2 is 3. Look at this. The numerator becomes 6 over the 3. Final answer for this is just the number 2. Pretty cool. Okay, there's one more type of problem that we have to look at. This is still talking about rationalizing the denominator, but now I want to talk about rationalizing denominators that aren't square roots, but are higher roots. So let's look at something like 8 over the cube root of 2. When it was square root 2, I just multiplied top and bottom by root 2 and moved on. I can't do that here, because if I multiply top and bottom by cube root 2, I still can't clear out my radical because I can't simplify the cube root of 4. So what I have to do instead is I have to think to myself, what can I multiply the 2 by that's going to get me a perfect cube? Well, the next highest perfect cube that I can see is 8. So why don't I do cube root of 4 to both sides, or rather the top and bottom. And now the top becomes 8 cube root 4. The bottom becomes the cube root of 8. And since 2 cubed is 8, I can rewrite that as just 2. Okay? And then I'm actually not done, because the 2 outside numbers, 8 and 2, reduce to 4 and 1. So my final answer is 4 cube root of 4. Okay? Let's try another one that's an even higher root. Let's do something like the 4th root of 6 over the 4th root of 2x. And let's make it 2x squared. All right, so I have to work backwards a little bit and think about getting powers underneath that denominator whose exponents are all 4s. So that way I can reduce. So I already have 2 to the first, and I have x to the second. So I want to kind of build powers of 4 here. So if I multiply 2 to the third, which is 8, I'll get my 2 to the fourth, which will let me reduce. And if I do x squared, I'll get x to the fourth, which I can also reduce. But if I do that to the denominator, I've got to do that to the numerator. Okay? So my top becomes the 4th root of 48x squared. And my denominator becomes the 4th root of 16x to the 4th. And this is perfect, so I can simplify it, which is the whole point of this. This becomes 2x. And the numerator just kind of stays 48x squared, because 48 I can't take out any groups of 4 in its factorization. Okay? So, you have some examples of these. Feel free to rewatch them. And if you have any questions, feel free to ask. Thank you, and have a good one.